Eindig zorgen.
Robert, we hebben een geweldige idee.
Dat is mooi.
De biomodellen zo langs van Cavalcante.
Ja.
We gaan proberen om met de matrix tijd.
Ja, ik kan also change the sheets.
Maar ja, we zullen het werken. Dat van
Is there anybody else who's coming?
Ja.
Is it going to be with the four of you, or is anybody else coming?
Yeah, it's going to be the four of us. Yeah.
Great.
Okay, fantastic.
Alright. We doen even de tafel weer aan.
Can we turn off the lights? Oh, but if it's... What? Oh.
Just this live because we won't show you. It's too dark for us.
That's good. I don't want my face in.
Okay, good afternoon, everybody. Today, as you know, we are going to present our report for our project for chip fabrication. And the group, we are calling it a team. Our team is composed by Dan, me, Daniel, Erik, and Guillaume. So I'm going to show you the table of contents that we have prepared for our presentation. Can you please? Okay, so I'm going to start presenting the team members and our background for this project, the motivation that took us to do this project, then the objective of the assignment. Then we had at least 2 weeks of pre-design phase until we reached the design phase on clearing, which is going to be explained by Guillaume. And then also the verification process through Flow Designer. And then we come up with a conclusion and some recommendations for future implementation. Then we state some references, and I'd like, if you have, please send questions, please write down the name of the slide, the number of the slide, and at the end we can clarify as far as we know. Alright? Alright. Okay, so to start up, I'm calling it not a group but a team, because we really worked as a team during these last 3 months. Yeah, 3 months something. Yeah. We had really great time doing this project, so we were meeting almost every week, like twice or 3 times. And as you can see, we are from totally different backgrounds, except for those 2 guys who come from, both of them come from physics. Guillaume comes from chemistry in her university, and I actually come from Brazil. There I do telecommunication engineering. I studied more applied for photonics, so we're kind of sharing lots of knowledge and ideas, and we're always working on feedback to each other, so it was a really great time that we had during this project. Impressive. So, our motivation, basically we are studying the minor in nanotechnology, and everything in nanotechnology is mostly at the end an application that will result in a chip fabricating a chip. So, chip fabrication for our minor is something really important, and that's why we really need for this project to finish at least with an idea of how to design a microchip. We are going to, this project was more about simulating than actually implementing it. So, because for actually implementing this project, we need to go to a clean room to do all the steps, and that's very expensive, we're just students. So, the main objective of this project was for us to have an idea of how things would be in the real world by doing it, by simulating with softwares and designing and so on. Alright, this next. So, the objective that was stated in our assignment was designing, developing, and testing a micro-optofluidic chip for spectroscopic measurements in nanofluidic volumes by using the evanescent field of the propagating light wave. So now I invite, that's not maybe clear if you guys were not from the field, but you are, and throughout our next slides we are going to explain the meaning of each of these words on our project. Alright? So I'd like to invite Erik to talk a little bit about our pre-phase and our phase of the design. Sorry?
I will. Could you go to the next slide?
Yeah, I got it.
Well, and here we see a short overview of the end of our result, which will be the chip. I'll explain very shortly in detail because Guillaume will go into further detail with the verification of Flow Designer. So basically what we want is a chip with fluidical channels and with a waveguide. So you can see here is the top layer and the bottom layer. We're going to make the chip out of 2 wafers. And the bottom wafer will have, the top wafer will have the fluidic channels, and the bottom one will have the waveguides. So, very shortly, how are we going to do this? As you can see here, we have a chunk of SiO2, which is glass, and we're going to etch away the channels for the fluidic channels. So that's basically it, and we're going to use CMP to flatten the surface. Well, that's the top wafer. It's pretty easy. But now comes the bottom wafer. As a waveguide, we've got silicon nitride, nitride, thank you, which functions as the waveguide. And then this is the cladding, the SiO2. So this is how we're going to make this is as the following. We will have a chunk of SiO2, glass again, and we're going to use lithography and dry etching to make the mold for the waveguide. So we got an empty plate, which will be the channel. Then we're going to use LPCVD, low pressure chemical vapor deposition, to deposit the silicon nitride, which will be the waveguide. This will stick out a little bit, so we're going to use polishing against CMP to flatten the surface. And then we have 2 layers. We're going to attach them to each other with bonding, something with temperature and something with time, which will be explained more in detail maybe. So yeah, that's basically how the chip will be fabricated. Please go to the next slide.
Yeah.
So this is the top overview how the chip will look like. You guys actually assigned us to do this, but I will explain shortly. These yellow things are O-rings, and the black dots inside are the entrances for the fluidical channels. So fluid can come into here. It can go all the way around this blue line, which is the fluidical channel. And then the red line is the waveguide, which is just underneath the fluidic channel. And then the evanescence part of the light can measure all kind of interesting things on fluid. Yeah, these things you see over here are the alignment markers for the wafer. Did I forget anything about this slide?
No, I don't think so. Yeah, just to clarify, the O-rings that are depicted here are just to show that the O-rings that are used for the input and output connections, that they actually fit around. So this has nothing to do with a mask, or it's just to show that they fit on the powder plastic.
Yeah.
And if I may, I just like to add something on the previous slide that I had forgotten. Can you just come one slide before? Just that the dimensions here are not real. So we are having here the fluidic channel and the waveguide with the same size, but actually it's 100 times bigger. So it's just
it's way much smaller than the fluidic channel.
It's just an overview draft, which was the first design.
Yeah.
Perfect.
Yeah. Can you go to the next one?
Yeah.
These are some details that are important for the dimensions of the chip. One of the most important things is the bend radius of the fluidical channel and the waveguide, which will be 2,550 micrometers. Yeah, and the powder blast is also 300 micrometers. I think those are the most important ones. Yeah, so I think you're the next one.
Yeah.
He's going to go into detail.
The waveguide here was just like in the assignment said that the waveguide should be 50 nanometers deep and the width of 1 micrometer. So that as well. And I will now explain something about the verification process within Flow Designer. So we begin with a substrate of 500 micrometers thick, which we use to spin coat a negative photoresist on top. So this is the bottom substrate that will contain the waveguide, as you will see. Then after exposure and development, by using the mask for the waveguide, you can see that this is a cross-section of one part of chip, like for example over here. And so you can see that after development the mask did its work, and then after dry etching by using reactive ion etching, we etch 50 nanometers inside the substrate. Next we remove the photoresist, and after that we deposit the layer, 50 nanometer layer of silicon nitride on top by LPCVD. And subsequently we use CMP to get rid of the excess of silicon nitride, which is on top of the substrate. And after that, we go to the second substrate. So this was the first substrate, which was depicted in the first slide. Then the second substrate, which we call the top substrate. On the front side, so on one side, we spin coated a layer of photoresist. After exposure and development, you can see the picture over there. We use dry etching again to etch away a 1 micrometer for the fluidic channel. Again, we use reactive ion etching in this case. And after removing the photoresist, you can see that the fluidic channel has been formed very nicely. And then we switch the substrate and we go to the back side. We spin coat a layer of photoresist for the powder blasting holes. Again, exposure and development, and after powder blasting, you can see that the holes go all the way through. And after this, we bond both wafers, and this is where Daan comes in.
Yes.
Continue on this.
So what you do finally after you powder blast those inlets and outlets, you of course remove the photoresist. And now basically what we have is 2 wafers, and each wafer contains one side of the chip, so the bottom or the top. And what we thought what we would do then is just bond those together using fusion, which has to be done at a certain temperature for a certain time. But due to lack of specifications and knowledge, we don't have the hard numbers, like we don't know at which temperature and at which time. But we do know that if you would do this in real life, it would be important to have those parameters set properly, of course. Next slide, please. So this is a cross-section of the wafers as they are bonded. What you see here, I'm not sure if it's visible, but this is the waveguide, and this over here is the fluidic channel. And as you can see, it's bonded good together. This is the most important area, of course, and Flow Designer does not show any anomalies there. So as a conclusion for this project, according to what Flow Designer gives us as results, we think it was a success. But one important thing that we found out almost near the end of our project was that initially we used LPCVD, PECVD, sorry, plasma enhanced chemical vapor deposition. And we thought it would be just fine. We thought it would be better than LPCVD, since that's according to the sheets that we were given, it has a faster deposit rate.
That's correct.
But actually, as we learned after we spoke with Robert, that PECVD will probably create something called voids, which is like empty space in your deposited material, as PECVD is a directional, non-conformal deposit method, as you can see in this schematic drawing. The red, like the red hills here, that's what you deposit, and what you will get in practice, apparently, is that you get voids, and we thought that that might influence the refractive index of the evanescent field. So instead of using this, we used the slower but more uniform LPCVD. And what I just said, Flow Designer verifies that our design as we have it now is successful. Some recommendations for if we would want to continue this. One thing is that halfway through the project we wanted to know exactly how CMP works, so also then we talked with Robert. In theory, what is in our sheets and in our data that we were given, it works, but in real life it's like your last resort. It doesn't work, it does not have the highest resolution, it does not have a very uniform effect on the entire surface of your wafer. So in theory yes, but in practice it will probably not work. Something else what we could do is optimize the chip dimensions. As you can see here, it's very thin, but this is the outline of the wafer. And we have 2, 4, 6, 8, like 10 chips here. We could make them smaller, design them smaller. Not too small obviously, because you don't want to exceed your specifications, such as the band radius, very important one. If we were to make it smaller, you could fit more chips on the wafer, thus reducing the cost per chip, since you obviously spend less time for each process step.
Yeah, and so just one thing to add also, One thing that we did not we did not attend exactly the requirements, the minimum requirements, was about the band radius, because it was, I think it was 100. Ours is 2.5 times bigger, so that's more visible for us. But in a real life, we would like to optimize these numbers. We don't optimize the material itself, so we'd have like kind of a little bit more chips on that way from that same space.
Yes.
Yeah.
So another recommendation obviously would be to actually make this chip and see how it works. Then you would test it, see how all the process steps work in a clean room. But obviously it's not a low threshold for us to walk into a clean room and go make the chip, which would be cool.
That would be cool, indeed.
That would be really cool.
Yeah.
So if you have any questions,
Oh, we got
please.
lots of questions.
There we go.
Thanks, gentlemen.
Thank you.
Good presentation from my point of view, of course, but there are also other experts. You started, Daniel, with an introduction in which you said, well, you gave us the assignment, so we should know what it's about, but there is somebody available right now over here who doesn't know about the assignment.
Yeah.
So the idea is that you convince people who are not into the detail in the project what the project is about.
Okay.
I'm wondering if you succeeded in that. So my question to Henry is, did you get a point?
Yes, I think so. I know what they're doing and what their plans. And, of course, I could have a lot of remarks, but that's part of the game, I guess. So you are, as far as I now understand, you just started. So in a way, there are many things. Maybe let's say backlights from other people is probably needed before you really go and step inside the clean room, because that's.
Of course.
Yeah, then there will be a process flow which will be tested thoroughly, depending on where you will come to be sure that you're not going to or reinvent the wheel, or doing things where you're already busy with your, let's say, application, whereas the creation of the device is probably, well, so if I look at it, there are many things I would say, well, I could talk about this one, but you don't know yet, so therefore I don't think it's necessary to do so. But,
May I ask you which company you're from?
I'm not from a company.
A professor?
No, I'm from the University of Twente and
Okay.
working in a clean room there. So let's say process flows and process documents are our, let's say, daily business.
What we didn't discuss was were the small steps in between like cleaning the wafer and inspecting.
Yeah, but that's okay. Let's say there are many steps where you have to look at if they are compatible with each other. And just, let's say you see now one step where you just change from PCVD to LPCVD. The trick now is that suddenly the temperature is going up. And that's not cool in this case.
Yes.
Because in that means that when you look further in this, then you have to look again at the total process flow. You will see that LPCVD, and after that, let's say, just going to let's say, try to bond the glass. That these temperatures could be quite, let's say, attacking each other. So that's not allowed anymore.
Yeah, we actually spoke with Robert about that, I think 2 or 3 days ago. And I think the biggest problem was with the bonding, that there would be a temperature achieved that would actually melt the SiO2. So it's
Well, yeah, that's basically sometimes what you want, that it locally melts and that it starts to get this bonding.
Yes.
Or at least that it changes with the surface. But it needs, that's in this case, probably a killer.
Yes.
Well, the chip is based on LPCVD and on direct bonding of your silicon substrate. So it's the assignment is based on chips which are existing and which they use in the packaging chemical.
Okay.
So just to give a small, so what I miss, but I will also give the word, of course, to Floris and to Robert. What I miss is kind of an overview why we want to design this type of sensors. What is the aim of the whole device which you're designing? Probably that's in the report, but you should also express it and try to explain it to the audience. So what's the added value? What is the application of the device? That's the first thing. Eh? So what do you want to do with the device?
Okay.
It is an online analysis of a fluid which you try to analyze, or a fluid which you fabricated somewhere or another. And secondly, so that's the aim of the assignment, and overall, because the course is chip fabrication, And the idea is that you get a feeling for what's necessary if you go into a clean room and to make a process flow, to go through the clean room with the highest speed, maximum yield, and lowest cost available. That's the basic idea. And then you should decide what type of fabrication equipment you should use, how to reduce cost, how to design such that you make as much chips as possible. And why do you do the things you didn't, like you described them? That's always the trade-off. So, and this kind of meetings, this kind of presentations should be to convince people that what you do is best, and also try to explain to people why you do it. And that's what I'm a little bit missing in this presentation. You sure understand what you do, but it's not really convincing to people who don't know, who don't have a clue, what's the added value of this research.
Method,
Yeah? You understand what I mean?
Yes.
Yeah. Okay.
You look. I think you really have the, which obviously is good, and the perspective
Of a client.
from the client
Yeah.
and the business and.
Exactly. So
Yes.
there are two things which in this case are very important, which I try to explain when I gave the assignment. First of all, trying to explain what the product is about, what's the added value of the device you're making.
Mm-hmm.
And secondly, because of the lecture which is underlying to this presentation, how to come to an optimized process flow such that people understand why you make the choices you made,
Yes.
and how to come to the design. And both are not very clear in this presentation, from my point of view. It doesn't mean it's bad, certainly not. It's a good presentation. Okay, floors.
Yeah, and one thing to really see that you understand the process very well, you showed alignment marks. Okay, can you show them again? And explain how they work.
Slide 8 or something.
It gives a good idea if you understand what you're doing and if the processes are that you're doing can be combined more or less. So I see 3 different alignment marks. What is what? What do I see there? The red is the waveguide. The yellow, you can explain.
Who can explain the origin of the alignment marks and where are they located in the process?
The original idea I had from alignment marks was just marks you put it on the wafer, just if I'm correct, exactly on the 0 line, like in the middle of the chip. So afterwards you can align both wafers correctly on top of each other so that everything aligns alignment markers, right?
Yeah.
That's why they got my head. Why they have different colors? That was just to make a clear marker. I didn't have any idea, right? Like
Because
it doesn't have to be like a waveguide, for example, just to make a difference between the 2 colors.
that's not true actually. I think.
Now, I've been told that when I have this red wave guide, actually here that also here will silicon nitride will be deposited.
Yes.
I thought. Yeah, that.
You have it in your mask, I think, as well. It's
Yeah, okay. It
That's
corresponds to the same
Yes.
mass. That's true.
yes, and that's the key here because then you know that you can align the next mask on your wafer, and that's very important. Otherwise, these will not overlap, or the powder blasted hole would have an offset or something.
Exactly. So that's the origin of the alignment marks. You align one mask layer to the other mask layer, and that everything
we
on the wafer will be in the same, in the proper position.
And we did spend one afternoon thinking about why and how.
And how many also,
And
because you had that big discussion, because at first we thought that only 2 would be enough, and then we started by 3.
It depends upon the amount of masks you use. So
Yeah.
every mask layer needs.
Yeah, in this case it's only 2 masks.
That was 3 actually. But that's
No, masks, no, I mean 2 layers. 2.
Oh yes, the wafer. Yes.
Floor, zit er meer vragen?
Ja, dat is met Robert.
Ja, Robert, shoot. Kan er iets? Nee? Zal ik het even doen?
Ja, ik heb er wel meer hoor, maar.
Cool. So first of all, so I was missing then the old, but this explained before, so that's clear. Those are the 2 basic points. Most probably the things which should be described are in the process flow, which should be part of your report probably. So you will hand it over to us, I assume. I didn't see anything at all about the use of the evanescent field. So you know what you're talking about. I get a feeling you really
Yeah,
understand
that
it.
was a big discussion also that we had about how much detail we should go into, because we really thought that it would be only for professors that are evaluating our assignment. But so we didn't talk about the waveguides, how they work out, and about why they are waveguides, about the choice of materials. But we can come back if you allow us.
Yeah.
Sure. Hi. Hi.
Come on in.
Can you come back to that first design of the
Come on.
Sure.
the pre-design? No, yeah, no, this one. Okay. So basically you have a waveguide in this case. For a waveguide you need basically like an optical fiber, two materials with different refractive index, with the condition that the inner material has a higher refraction index than the outside material, so that it can keep light inside through the phenomenon of total internal reflection. So that was the main decision why we took, what's it, PLC? I always forget that. Yeah, why we chose that, because if we had that kind of deposition, it would have some gaps here. Then instead of two different materials, you would have three, and then the refractive index at these points here could change, and then you wouldn't keep total internal reflection anymore, and then it wouldn't behave as a waveguide anymore. So the main point is to have this material here, silicon nitride. Silicon nitride, it has a slightly higher refractive index than silicon oxide to keep the light as a waveguide. That band we saw. Can you go to the top later? Next slide. Yeah. As you can see here, this is the waveguide, so it has a band in here. Of course, we have a limit of this. This limit so that the light doesn't escape, because it still needs to reach an angle here.
Yeah.
That's why I mentioned that we did not respect the minimum value. We could even make it like a little bit smaller, a little bit closer, like this 100. Which was, I think, 250, the distance, so it could decrease a little bit more so that I could have more chips. So the properties is basically this light is going to be inserted to that way through a laser. It will be in contact with this liquid that will be inserted here in the blue channel. During all this stage and this stage, it will measure through the evanescent field. The evanescent field is basically, I could draw it here, like for example, if you have this surface of one material.
You can draw it, right?
Yeah.
It's behind you.
Yeah. So for example, in that case, I have the fluidic channel that's here. Let's say material 1 and material 2, which is the waveguide, which has a refractive index, let's say A, which is higher than B. And then what normally happens that wave that touches the surface, we are told in school, in high school, that it comes back absolutely, but actually it surpasses a little bit the surface at a micro scale, nanoscale, some nanometers. And this is the evanescent field that we have. So it's like the light's trying to escape, but it's attracted back to that medium which has a more refractive index. And then it's just a slight window, it's just a very small window that we can use to put something here to measure that. And then basically what this chip is doing at the end is to get in contact, this liquid is going to get in contact with this light that is escaping from the evanescent field. And this light is going to measure the absorption and other properties of this liquid. That can be anything in our body, or so basically for biological purposes.
Okay. So you understand it, that's clear, because you got a telecom background, so you should already know. Besides, you already got the courses of Gerard on integrated optics, so they should be clear. But in the presentation,
The immersion presentation.
you should have
that's the
shown
key,
the
yes.
evanescent field principle, and also how deeply it penetrates.
Yeah.
I would also would like to hear the wavelengths you're using, because it's also which is of great importance for the application.
Yeah.
Okay. So these kind of things are of
It would have been very valuable in the presentation.
exactly.
We didn't mention anything about the wavelength, because I think it really depends on what kind of fluid you are using, and you don't know actually what fluid, so you need also to,
Exactly.
okay, you're using for blood, for urine, or something like that.
But that's a consideration which I would have liked to see in the report, because
Yeah.
it also shows that you understand what the application is.
You could make a table, yeah, like for this kind of fluid, yeah.
But okay, for next time, those are things which are major important, so that should be in the presentation.
Okay.
And you don't have to give a calculation how you calculate the depth of evanescent field, it just shows during the presentation.
Yeah.
It's in the order of 100 nanometer, 200 nanometer, maybe half a micron. And also, what's the consequence for the layout for your microfluidical channel, for instance? Because should it be 100 micron deep, or should it be half a millimeter deep, or should it be those kind of things? Okay, you understand what I mean? Secondly, Kom er maar nog heen.
Mag ik erin? Want ik stoor verschrikkelijk natuurlijk.
Sensing window. You never described the principle of a sensing window. So you don't cover your optical waveguide. You close it by your second substrate, probably.
Yeah.
So you got two glass substrates, one with the integrated optical waveguide, one with the microfluidic wave. You combine them, you fuse them, and then the oxide of the top wafer covers the optical field. Is it correct?
Yes.
Okay, so there where you enter into the microfluidic channel, there you have actually an open window where you can measure. Okay, that's clear. All right. Next
What's
question. Why is it designed like you have it right now? Why is it a U with a U? I know it's in the vacuum carousel, it's in the available chips.
Yeah, we had thought of lots of, after I talk with you guys can add something that's for project, please. But we started for our goal here was to have the maximum amount of contact between the two channels.
Okay.
So we had a chip, needed to be small, and we'd have two channels, and they would have to be the maximum, how do you say that? The maximum
Like
for the
shared
maximum
surface.
length in contact. The most, the
Most
biggest,
contact.
of course, yeah, the
The
biggest
impression
surface
length.
contact.
In the beginning, we thought also of
Yeah,
a chip that had just one line with
Yeah.
the fluidic channel and the waveguide overlapping. Then actually we thought that the design we had seen already, like this, we had more overlap of both channels and more that the measurements would be
More sensitive.
much better, more sensitive, and also the both inlet and outlet will be on one side, and for the waveguide will be on the other side, which would also be a big advantage.
Practical.
We compared the sum of the lengths that we could have in each of the various designs we thought of, and this one would be the best one for us.
Okay, next time in your report, when you try to actually, what I always tell to students is that you are the managers of the future. Eh?
Yeah.
So now you're now still student, but in 1 year or 2 years from now, you will be in a leading position in companies. You have to explain to your employees why you do what you do in a company. So you should convince people why you make this selection.
Yeah, that's
So
right.
now you understand. Now you try to explain to me, but it should have been in the presentation.
Yeah.
Why you make this choice? Because in the end, it could be make a difference between a product which can be sold in large quantities or something which is too expensive to fabricate, which means that your company goes bankrupt.
Yeah.
So please try to explain.
Ask yourself why all the time.
Exactly. Ask
After
yourself
everything
why.
you do, you should ask why you do it, so you can
Yeah.
Yeah, I think we miss it because for us it's something that's so clear that we need to justify that, but actually we need to justify everything.
Because this is of course a major consideration. The chip should be as sensitive as possible.
Yeah.
But how does it? Why does it create a design like this, or what does it has a consequence like a design like this?